Okay, so we're going to begin to do these Ampere law problems for straight current carrying wires. So the first one gives us some information. It says superconducting wire will return to normal state when a magnetic field at its surface exceeds 0.1 Tesla. So B is 0.1, B equals 0.1 Tesla. If the wire has a diameter of 2 millimeters, diameter equals 0.002 meters. What is the critical current I that can carry without quenching the superconductivity? Okay, so here we can set up the equation we derived on the other page. B of a straight wire is mu naught I over 2 pi r. And r is how far we are from the wire. In this case, we're going to be at its surface. So we're going to have 0.1 equals mu naught, which is always the same number and can be found on the previous page. 4 pi times 10 to the negative 7th. Our current I divide by 2 pi and our radius, so take our diameter over 2. Cool. As we begin to simplify, these 2's cancel, so do these pi's. Then we can solve for I. And I get a current of 500 amps. Onward. So we have a coaxial cable, which means that there is a inside wire and an outside wire. And as you can see, they carry currents in different directions. Outside and inside. Outside is to the right and inside is to the left, which means they will make magnetic fields that are in opposite directions. So if we look at the inside, take your thumb and point it to the left, and our current is going to wrap around like this. Our magnetic field is going to wrap around like this. And then if we take our thumb and we point it to the right to express the outside magnetic field, it's going to wrap around like this. B out, B in. So you can tell those magnetic fields are in the opposite direction. So this is what can be referred to as magnetic shielding. So we can run a wire with a strong inner current, an outer current, and theoretically be able to cancel those magnetic fields. So let's see here. When currents I in and I out are equal, the coaxial line is considered a shielding line. That is its intended mode of operation. For the situation, derive an expression for the magnetic field at the points outside the central solid conductor, but inside the tube. So this is the region that I drew in pink here. So what we're going to do is make an Amperian loop right here. So we're going to take Ampere's law, B dot dl equals mu naught, I net that flows through. And on this side, just as always, we're going to end up with B times 2 pi little r, where r is how far we are, somewhere between A and B. Then we're going to have mu naught, and the I that's inside here is I inner. So the expression for B on the inside simplifies to mu naught I inner over 2 pi r. Now let's take B outside. So on B outside, when we set up Ampere's law, you're going to have two currents inside to consider. So integral of B dot dl is mu naught I net. And so here we're going to make a Amperian loop, B times 2 pi r, just as we always do. R will now be outside the tube, mu naught. But when we write I net, we're going to enclose I outer and I inner, and they're going to be in opposite directions. So B will be mu naught. Then the difference between I outer and I inner over 2 pi r. And if the two values are equal, this should simplify down to 0, which is the idea of magnetic shielding. Okay, next we're going to carry two long wires as shown in this figure, and they have currents in the same direction, but I1 is 10 amps. This. Oops, I guess it doesn't say which one's I1. I1 is 10 amps. I just assume that's at the top. And I2 is 20 amps. So in order to find the magnetic field, I'm going to use my right hand rule. So I'm going to take my hand and I'm going to put my thumb to the right to mock the direction of that current, which they're each to the right. So I can use this for each one. So here I get my magnetic field is going to curl around. So it's going to go underneath, behind, and in front of my wire. Underneath, behind, and in front of my wire. Now, an easier way to write that is that it's coming out on top of my wire and in below my wire. That same thing will be happening down here, right? I could take this picture and I could reevaluate down here. It's going to be that same thing. My I points to the right and my B goes under, behind, up, and in front. So under, behind, up, and in front. That can also be just right out and in. Now, as you go further and further and further from the pink wire, your B is going to get smaller and smaller and smaller and smaller. And as you go further and further and further from the green wire, same thing, right? Your B's from that green wire get smaller and smaller and smaller and smaller. And so let's evaluate this point, P1, at the center of both of them. So you need to think, are we going to add those B's together? B net, remember, this is vector addition, or are you going to subtract? So they're in opposite directions. So let's take our larger B, which is probably going to come from the pink wire. B, it's directed outward at point P1 because P1 is above the wire and there's outs above the wire. And then we're going to subtract off the B that's in from the green wire, the 10 amps. And then we can just write out the equation for each one of these. So we can write mu naught I over 2 pi R minus mu naught I over 2 pi R. And then we can replace our R's with this value A, which is what it's given, and we can replace our I's with the two numbers in the problem. Let's see, so I. So here we're going to have 20, and here we're going to have 10. And so this will simplify down to mu naught 2 pi A and 20 minus 10, which is 10, and the pink one is larger, so we'll have an outward directed B net. Okay, so we're coming back to a very similar problem as we just did in 3. This time we're going to have our currents in the same direction and they each have the same value. We're just going to leave it as I. And in the previous problem where we put our right hand, we realized the B circled around. And so in each one, the B goes behind, out, back in. And then same thing here, out and in. And at this region, P1, the fields are just going to cancel because they're the same. So let's just do P2 together. So as you get further and further and further from the purple wire, your field is going to decrease. And you're also going to have an inward field from the green wire, right? So smaller in, and smaller in, and smaller in. So at this point, we're actually going to have a B net that is going to be the addition of the B from the green wire and the B from the purple wire, and they're each going in the same direction. And so what we can do is we can write out each term. So mu naught I over 2 pi R. R is how far we are. So we're 1A, 2A, 3, 4A. So here we have 4A away. And for the purple one, we're going to have mu naught, same current I over 2 pi, and we're only 1, 2 away. So we're going to have 2A here. When we add those together, we're going to get our total B. So it's going to be mu naught I, and then we'll have 2 pi, and then we have 1 over 4A minus 1 over 2A. And that's going to simplify to plus a half plus a fourth, and a half plus a fourth is 3/4. So we're going to end with, this is our B net. B net equals mu naught I over 2 pi, and then a quarter plus a half, which is 3/4, and A. The net B will be inward. All right, so here's problem 5 on page 4, where we're practicing applying our Ampere's law for a straight wire. So here's Ampere's law for a straight wire. And these are the symbols we're going to be using because we're looking at wires looking at like a cross-sectional area cut of a wire. So if we see this X symbol here, that means that the current is going into the page, and this dot means the current is coming out at us. So if we take our first one, we're going to take our right hand and we're going to kind of put our thumb in the direction of current, and we're going to do that 4 times. So it's going to look like this. 1, 2, 3, 4. And we're going to discover that the magnetic field, tracing our fingers, wraps around each one of these just like this, just like our fingers show. And so that magnetic field, as we realize, will change depending on how far away we are. So we're interested in this center point right here. So let's go ahead and make those a little bit bigger. So we'll go ahead and do this top left one. And we'll make this B just a bigger and bigger in a circle. So we'll make a B, bigger. And then all of them, right, put some arrows on it. Then what we're going to do is we're just going to highlight that spot of interest right here. So at the center point, I'm just going to take the B that touches that point. So you'll notice that, let's erase anything extra here, entire stroke. So the distance R and this B vector are at 90 degrees because the B we drew in is tangent, touching at a point. We can do the same thing. The next one, let's draw it in blue. So again, we're going to make these circles that are going counterclockwise. We're going to make them bigger and bigger and bigger until they hit that spot that we're interested in, and we're just going to highlight in one of our vectors. Let's take out anything we don't need now. Okay, again, our R and our B are completely perpendicular. We're going to find that in each set of these problems. We'll do the next one. I'll draw the next one over here in pink. We're going to go ahead and draw that circle. You can draw it bigger and bigger until it hits that spot of interest and highlight it in. Take away anything extra. And our last one, let's do, I don't know, purple. So our last one, again, draw that circle in. Draw it bigger till it hits that point and highlight it. And then take away anything extra. Oops. It was like this, right? Okay. I know you can't answer me, but it was like that. So then let's think of the value of these B's. Every one of these B's that we drew has the same mu naught. It's constant everywhere. All the currents are carrying the same value I. And then our distance R, what is that? This R. Well, R is how far the current is from the point that we're talking about. So this distance here is R, right, which I highlighted in earlier. So R is going to be part of a triangle that we can find here. This is half S, and this is half S. Oopsie, half S. So when we want to find the hypotenuse there, we can just do the square root of S over 2 squared plus S over 2 squared. And that can give us our R. But now looking at the vectors, just looking at vector addition, you'll realize that all these B's are just going to cancel each other out. And so it doesn't really matter what R is because we just come up with B is 0 here. Okay, let's go through and you'll do the next set. I'm just going to pop the answers on there of the vectors from each spot. Okay, so now that we've drawn in our vectors, there's only 2 actual ones of these are going to have any values. So let's focus on B and D. The other 2 just cancel out to be 0. So in location B, you realize that the green and the pink vector will cancel. And the blue and the purple vectors are going to add together. So how big is one of those purple, is the purple or the blue vector, right? Because you're going to have purple vector, you're going to add blue vector on top of it, and we'll get our resulting vector, which is B total. So here, B total. So our total resulting is just going to be the addition of the blue and the purple. And if we want to know, let's just go ahead and find this R value really quick. So R is, that's S squared over 4 plus S squared over 4 is S squared over 2, and then square root of S squared over 2 is just S over root 2. And so our B's are each mu naught I over 2 pi S over root 2 plus another one mu naught I over 2 pi S over root 2. And we'll add those together and we'll get our B, and we know the direction it's pointing is 45 degrees. 45 degrees. So the summation of these two B's is just mu naught I over, instead of a half and a half, we just have pi S and flip the root 2 up to the top. There you go. So that is our magnitude of our total resultant B, pointing like this at 45 degrees. Okay, this next one is cool. So if you look, all our vectors are important here. And if we add these all together, it's going to look something like this. So you're going to have pink vector, let's see, pink vector added on top of green vector, purple vector added on top of the blue vector. And then you can take this vector and you can add it to that vector, and you get a total resulting vector that's only in the x direction. Whoa! Okay, so if we look, our y components will cancel out. So, and all of these have the exact same identical value. So let's just take the x component of each one and we'll add it together. So we're going to find the x value of the green, we'll add it to the x value of the pink, and then we'll add that to the x value of the blue, and we'll add that to the x value of the purple. So let's just find bx, and we'll multiply it by 4, and that will get us our resultant b total. Okay, so you already know b from above, right? B is just one of these values, mu naught I over 2 pi r, and r is S over root 2, as we found earlier. So now to get the x component, it's just at 45 degrees, so let's just take cosine of 45. Let's simplify that, mu naught I over 2 pi S over root 2, and cosine of 45 is root 2 over 2 in terms of special triangles. And then what we're going to do is we're going to take 4 of those babies. So simplifying all of this is going to get our B total, our B resultant, and these root 2's is going to flip up to the top. And then these just become the number 2, and this whole thing becomes value 1. Then you're going to have 4 divided by 2, which just becomes 2. 2 mu naught I over pi S. And it's 0 degrees, it's in the x-axis only, so I had. Awesome job.